Good afternoon. Today I would like to discuss my PhD thesis, robust Sentry-Based scheduling algorithm. This is a research work conducted under the direction of Professor John Malicious and aims to provide both candidate efficiency and fault tolerance within the wireless sensing network. I'll start with the motivation behind this research and how this problem came into form. Then I will talk about the first piece of the work, energy efficiency Sentry-Based schemes. And then I will talk about the second piece of work, the secure Sentry-Based scheme, which basically research on how a Sentry-Based scheme react when there are malicious nodes within the sensing network. Then I will wrap up with talk with a presentation with a summary related to work. So first, I will talk about the current state of the wireless sensing networks. So about a decade ago, wireless sensing network is still a term most people only heard in academic community. Now, we are seeing more and more wider spectrum wireless sensing network application in more and more areas, like internal office, in which sensing network can help provide the best light condition for each individual as external sunlight condition change during the course of the day. And in this particular picture, this is the application for forest fire detection, where the sensors are spread from the airplane to the forest, and each sensor is equipped with thermal sensor. So whenever there's a fire takes place, the sensors around the fire spot will detect the extreme temperature. It will send the collections to the base station so that the quick action will be taken. So even though such network has been in advance, there are still a lot of challenges remain for wider adoption. So we still need an efficient mapping routing protocol in the presence of random node failures. And then we are looking for a program model from where people are looking for a branded program model we usually see in the PC, even smartphone. And then there's a security and privacy. This is for the topic within any network system. And then scalability. We want to see how the system operates as the scale goes up. But one particular issue we're interested in the longer operation lifetime. So what is the obstacle to the long lifetime? First, most sensor nodes are driven by battery, and it's not rechargeable. So take this mic 2 sensor as an example. If it's an active mode, the AA battery only can keep running for about a week, which is obviously not enough in the application, just like fire protection, because we don't want to deploy the sensors once a week, even once a month. And then there's random node failures. Look, if we look at this mic 2, it's very compact. However, it has sensor board, it has a radio transceiver, even has a CPU, and has its own operating system. So the package is relatively cheap, and the internal hardware failure is really norm rather than exception. And then when it fails, no one cares about it, because once we deploy sensors, most likely it will be not attended, and no one will bother repairing it. So the common practice is, so normally sensing network will deploy with high redundancy, and then people keep the redundant nodes off to conserve energy, and then turn the redundant nodes on when they need it. That way, people think it can prolong the network lifetime beyond the lifetime of individual node. But here is a problem. Why? So the rationale behind this shift-based practice is, normally the operation power is 3 orders magnitude less in sleep mode than in active mode. But the power is comparable in reception mode and transmission mode. So that means even though we keep a node idly, it still consumes pretty much the same power as in active mode. But if we turn the node into sleep mode, it consumes a lot of energies. And so like I mentioned, so people deploy, why people deploy the Sentinel with high redundancy? Not because they want to enable this shift-based practice. Instead, they want to keep all the nodes on so that when several nodes die, the whole network is not affected as much as when only a minimal set of active nodes is active. So here we have a problem. For bad service quality, we want to deploy with high redundancy and to keep all the nodes on to compensate the random node failure. And on the other hand, we want a longer service time. We turn off the redundant nodes and keep a minimal set of active nodes active. So whenever one of those minimal set of active nodes die, network service could be disrupted drastically. So the goal of our research is that we are going to provide a long-lived, robust sensor networks, even in the presence of random node failure. Before I go into detail of our article, I will introduce the net sense network model we use in our research. First, we adopt a grid-based coverage model. So we partition the whole network into square grids, and then we assume a multi-hop network, and the shortest path routing is available to the outlet. And then we have this sensor model. So we adopt a disk-shaped model. So the sensing area will be a disk-shaped area with a node at the center and the sensing range and the radius, and this shape indicates. So any grid points fall into this shaped area will be able to be sensed by the node A. And also we assume it's a symmetric node link. So any pair of nodes could talk to each other, and also each node has its location where they can get the location either through GPS or through in the localization algorithm. Also, we introduce the concept of sensing redundant set and again. So sensing redundant set, so a node sensing redundant set is a set of nodes that have coverage overlapping with the current node. Take this example. So in this table, the first column is the node ID, and the second column is the grid points each node covers. So in this example, node A, the sensing set, consists of node B, C, D, F, Y. Because node B, C, D, F all covers all certain grid points, node A covers. So that's what we call it. So that's why these nodes are part of the A sensor redundant set. And then we have GAN. GAN is an enhanced subset of sensor redundant set. In any GAN, any node in the GAN, they could collectively cover all the grid points the current node covers. Again, take a look at B, node B. Node B covers grid points 1, 2, 3, 4, 5, which includes all the grid points node A covers. So B alone constitutes a GAN of A. And then node C and E. Node C and E combined cover all the grid points node A covers, but any one of them alone cannot cover all the grid points it covers. So the node has a GAN list B and C and E. Now we'll talk about the first Sentry-Based scheme, P-Sentry. So the motivation behind the P-Sentry is we need a quick response when active node dies. So the approach will be we keep a subset of redundant nodes always alert, which we call persistent sentries, and monitor the active node. And then keep the rest of redundant nodes sleep longer to conserve energy. So this is the workflow of the P-Sentry. First, at the very beginning, all the nodes are active during the initialization period. During this initialization period, all the nodes will broadcast its locations, its IDs, and then it's the grid point it covers. So nodes within one hop or two hop will exchange information. Each node will establish its graded point list and its node list and its sensor redundant set. After that, they will elect the initial set of active nodes in a distributed fashion, which I will talk about later. Then after the initialization period, we go into the working phase. In here, first the active node make a selection of the persistent sentries that will protect the active node. And then active node will generate a schedule for the non-P-Sentry nodes. After the active node make a selection and generate a schedule, the redundant node will go to sleep as scheduled. Then it will wake up as scheduled to probe. And every time it wakes up, it will probe if the active node is still alive, and if the P-Sentry nodes are still alive. If any one of the P-Sentry nodes dies, it will back up the existing P-Sentry nodes for a particular active node. So for the P-Sentry nodes, it will exchange a heartbeat signal with the active node, so that both active node and the P-Sentry could be aware of each other. And when the P-Sentry nodes detect that the active node they are guarding has died, it will become active. And once they become active, it will again gradually make a selection of its own P-Sentry nodes and generate a schedule of its redundant nodes. So this working phase goes on until the nodes, all the nodes run out of edge. So among what happens during initialization phase, one particular thing I will talk about is an actual initial set of active nodes. This is so during this in this distributed election process, each node starts a random backup time and collecting active messages from its active neighbors. And then when the timer fires, each node will check if all its graded points are covered by its active neighbors. If yes, then this node does not need to be active, so it will be asleep. Otherwise, it will broadcast the active message to pronounce it will be active. And then when this process ends, basically when the time of every node has fired, every node will figure out its operation mode. And then we will have an initial set of active nodes. So P-Sentry is rather straightforward, but there are still some key points we want to focus on. First, criteria for the selection of P-Sentries. So theoretically, there could be a lot of criteria like remaining energy, capability in terms of coverage and the packet forwarding, and also the locations. So it could be any application-specific criteria. So in our simulation, we use the remaining energy as a criteria, so that active node, the P-Sentry nodes could outlive the active nodes in the ideal environment. And then the sleep time of the non-P-Sentries. So we need to outbound. So the outbound for the sleep interval for non-P-Sentry nodes will be the lifetime of the active node, because once the active node dies, the schedule those non-P-Sentry nodes are following up are basically meaningless. So those non-P-Sentry nodes need to wake up before the active node dies to get a new schedule or become P-Sentry or even become active nodes. And regarding the active node lifetime, we can estimate the lifetime of the active node based on historical traffic information and other factors. And so one question we will ask is, so every time an active node dies, we will more than one Sentry node take over become active. So as it goes on, there will be more. The number of active nodes will increase exponentially. So to address that issue, we will have a threshold. We will have one more condition before Sentry node contacted. So that is the number of active neighbors of a particular redundant node should be less than the threshold active number. So this number could be an experimental parameter we get from previous one observation. So P-Sentry is really the first piece of work I worked on as a PhD student. So now here comes the R-Sentry. So the motivation behind the R-Sentry is all the previous works didn't provide a guarantee of average coverage recovery time, and they are not configurable. That's for sure. And then no few of the existing work take into account the premature node death. So all they assume is the active node dies only when they run out of edge. And then the issue with P-Sentry is energy wastes on persistent sentries. So like I mentioned, the radio transfer on the sensor node, which is the main energy consumer on the sensor node, have the same power when they're in the reception mode as they are in the transmission mode. So that means the P-Sentry node pretty much consume the power at the same rate as the active nodes. So the approach is we want all the redundant nodes to contribute equally by rotating as a unit of the gain. So the gain is scheduled to wake up in turn to check on the active nodes. So the goal of this work is first, of course, we want it to be energy efficient. We want to extend the network. Secondly, we need a configurable average service loss time in the presence of the random node failures. So like P-Sentry, this is a two-phase scheme. First is the initial phase. During the initialization phase, again, it will initialize the neighbor list, data point list, sensor redundant, and again. Then we will elect the initial set of action nodes in the same distributed fashion as we use in the P-Sentry. Then we'll initialize the gain schedule table, which is used to record the next wake-up time for each gain. After the initialization phase, we have the working phase. During this phase, at the very beginning, at the end of the initialization phase, when every nodes are up, the initial set of active node will statically establish the gain schedule for its gains. Then, so the gain will go to sleep and wake up as scheduled. When they wake up, they will send out a probe message to find out if the active node is still alive. So if they're alive, that's fine. They will go back to sleep with a new schedule from the active nodes. And then those redundant nodes, they could die during sleep. So the active node will adjust the schedule as they detect that certain redundant node has died. And then the last process is when the redundant node takes over as active node, it need to dynamically establish the gain schedule for its own redundant nodes. So really the schedule is the essence of the R-Sentry. So I will talk about the basic idea of the R-Sentry, of the schedule. So like I said, again, wake up by rotation, and consecutive wake up in R-Sentry is delta apart. That way, anytime an active node dies, it will be detected in less than delta time. So each gain, so because all the gain wake up in a round-robin fashion, so each gain actually just needs to wake up once each round, which is the number of gains times the delta. And In other words, the sleep interval for a particular GAN is n times delta. And now let's look at this example. So this is the active node A's GAN table, GAN schedule table. So the first GAN BC is scheduled to wake up at 1200. The second GAN wakes up at 1500. The third GAN wakes up at 1800. The fourth GAN wakes up at 2100. So the wake up time is 300. So the wake up time is 300 part, which is the delta in this example, and the run time will be 1200. So if we look at the example, based on current gas field table, BC wakes up at 1200, BC wakes up at 1500, BE wakes up at 1800, EF wakes up at 2100. Then this is the end of the one run. So when the new run starts, which in this case when the BC wakes up, when the BC wakes up at 2400, it will get a new schedule from the active node, which will be the current time plus the run time, which is 1200. So the next wake up time will be 3600. So we can say the same for DC, for BE, for EF. So this run-based function goes on and on until some of the game nodes dies, all the active node dies. So let's look at what happens when a redundant node dies. So failures happen to active nodes as well as redundant nodes. The active node needs to adjust its GAN schedule table when the GAN dies or dissolves, so that it could keep the delta, keep the average loss time within the delta, coverage loss time within the delta. In R-Sentry, when active node detect down here from the redundant nodes within one run or two runs, it will conclude that the redundant node has died. So it will adjust to the GAN schedule table. So if we look at this example, in this example, the delta is 300, so run is 900, and so the redundant node D failed at time 1000 by a failure.
Hello?
We have some committee members calling in.
Yeah. Good. Hello?
So at time 1000, D dies, right? So here the active node has no idea the D has died, so nothing will change to the GAN schedule table. Then at time 1500, node D and E are supposed to wake up. However, the active node is only here probing from node E. The active node wants to be conservative, so it will wait. It will wait and not take any action. Then at time 2400, again, node D and E should wake up. And however, again, the active node doesn't hear from the node D. Then the active node decides to take action.
Wait, can you hear us?
Yeah. Okay. Good. So the active node decides to take actions. It will remove the GAN of DE from the GAN schedule table. So then we have two GANs, which means the run will be reduced from 900 to 600. So next, at time 2700, GAN FG wakes up. And because at this time the round has been reduced to 600, so we will put the next wake up time of the GAN FG to the 2700 plus 600, which will be 3300. Then at time 300, when GAN BC wakes up, we will increase the next wake up time to 3600. So this way, we again gradually ensure that every delta there will be again waking up to check on the active node. So far, active node is always there. It never fails. Then let's check what happens when active node fails. And one of its active node, one of its redundant node, A takes over. So at time 1200, previous node A, previously redundant, becomes active. So at this time, the GAN schedule is empty. Why? Because when the redundant node is in sleep, there's really no association established between this redundant node and its potential redundant nodes. And the redundant nodes have no idea how many the previous redundant nodes have no idea how many redundant nodes it will have when it becomes active. And the redundant node, those redundant nodes of the new active node are still following the schedule from the previous active node. So we need to gradually fill the schedule table for new active node. In R-Sentry, it's rather straightforward. So let's see what happens. At time 1300, node B wakes up. And the active node searches the GAN schedule table and finds out there's no schedule for node B. But B is part of its GAN. So it will assign the next available wake up slot to GAN BC. Because the count time is 1300 and the delta is 300, so the next wake up time will be 1600. Then at time 1400, node C wakes up. And again, the active node will search the GAN schedule table and it finds out C is already scheduled as a member of the GAN BC, so it will do nothing. It will just send the same wake up time 1600 to node C. And then at 1500, G wakes up. Since G is not part of any GAN of the new active node, so nothing would happen to the GAN schedule table. And then at time 1550, node D wakes up. So node D is part of the GAN of DE, and this GAN has not been assigned a schedule. So it will again assign the next available wake-up slot, which will be 300 plus the latest wake-up schedule. Then at time 1600, node B and C wakes up. And again, currently we only have two GAN against the table. So we will ask GAN B and C to sleep for 2 times delta, which will be 600. So the next wake-up time will be 22 seconds.
So is there some notion of what defines the adequate coverage? Is that if it's 2 nodes be up?
I'm sorry?
What is good enough? Like is 1 node being up good enough?
So
I'm
here,
sorry I jumped in the middle of it.
okay. So GAN. So previously we defined GAN. GAN is a subset of the redundant nodes that could collectively cover all the grid points the active node could cover. So when the active node dies, those GANs could cover all the coverage lost due to the death of the active node. So, but we want to limit the size of the GAN. So if we have to go with the GAN of size 3, then we can have the GAN of size 3. Here we make it 2 for implementation purpose.
But somehow it's not more complicated if it's 3.
Definitely it will be complicated, and the benefits will be not as much as expected, which we'll talk about later. So at time 1700, node E and F, node E wakes up. So again, active node search against the table and find E in part of GAN, but he doesn't have a schedule yet. So we assign the next available wake up slot, which will be 2500. And then you go back to sleep. And at time 1800, node E wakes up. So again, node E is part of GAN that has been scheduled by the active node. So it will simply send the counter schedule to node E, and so finally, new active node establishes its GAN schedule table, so it can start being protected with the guarantee that its death will be detected within the delta. So, in all the 3 scenarios that I have talked about, we assume there's only one active node involved. But in reality, active nodes could be shared by redundant nodes, and which means a redundant node could receive the schedule from multiple active nodes. So in this scenario, how do we proceed? In R-Sentry, each active node schedules independently, regardless of how many redundant nodes it shares with other active nodes. And redundant nodes, however, keep a sorted list of wake-up schedules, and it always follow the latest, the most imminent wake-up time. And as the redundant nodes wakes up, it will update this list and it receives the new schedules. So we evaluate both P-Sentry, R-Sentry schemes in our homegrown discrete event simulator. So in this simulator, we assume ideal communication links, and it's largely symmetric. And it doesn't intend to simulate the network stack details. We believe our protocol is orthogonal to any layer in network stack, and plus we evaluate all schemes within the simulator instead of compare against any real-time network aspect. So also we assume it's a propagation delay is negligible, and the latency and the power consumption radius which is negligible. And in our simulation, we assume a 50 times 50 field, and the grid size is 1 times 1. And unless stated explicitly, we have 600 nodes. And the energy, the initial energy each node had could sustain the nodes for 2050 to 2700 seconds in reception mode. And the sensing range is 10 meters, and the communication range is 20 meters. And the delta we assume it's 15 seconds. And the GAN size is 1. So in order to model the fact that the nodes could die before it runs out of energy, we introduce a catastrophic failure model. In this model is pretty much defined by 2 parameters. Firstly, the failure period, which is the mean time between consecutive external catastrophe events, and then the failure percentage. This is the mean percentage of the living nodes that fails in a particular event. So this is a rather coarse-grained model, because any node affected will just completely stop functioning. Also, we use performance metrics as a coverage ratio, which is the percentage of grid points covered, and in the theory network lifetime. This is a duration the network lasts until the coverage ratio drops below theta and it never comes back. We want to use this. We want to use this metric to measure how the system could recover from the coverage loss. And then we have a coverage recovery time. This is the duration from the coverage loss due to the death of active nodes and to the recovery because the takeover of the redundant nodes.
So is it the catastrophic event that is causing a bunch of these nodes to fail?
Yeah, that's one of the reasons. The other reason is the energy. So when each node runs out of energy, it will let to.
But like that first failure percentage thing as percent, the second bullet,
Yeah.
those are nodes that some number of nodes that when you have the catastrophe, that it destroys some
Yes.
number of the nodes.
Yes, but on top of the death caused by the low battery.
And you just kind of randomly just destroy them with probability of percent.
Yeah.
Like there's no spatial correlation or anything.
No.
So what kind of catastrophes are you thinking about?
Oh, it could be like take the example of sensitive deployed in remote rainforest. So like the sudden rain, the rain, even stomped by animals could be those catastrophe events. So we compare our scheme against the P's. The P's is a relatively well-known shift-based scheduling protocol. It shares a similar goal with us, that it provided the extended lifetime even in the presence of the random Sentry-Based. So in P's, every redundant node wakes up. When it wakes up, it will send a probing message. It will try to probe the active node within the certain range. If it doesn't receive any reply message, it will become active. If it receives a reply from any active node, it will again go back to sleep for a random amount of time. So the catch of the P is the active node counts the probings that it received from all its neighbors, and then send its observed probing rate back to the probing redundant node. So the probing redundant node will use this observed aggregation probing rate to generate a schedule so that overall the probing rate experienced by the active node will be close to the desired probing rate, or it will achieve the desired distance between consecutive probings, which is a reciprocal of this lambda. And in this example, in P's, actually the reciprocal of the lambda is similar to the delta parameter we presented earlier. So, but the disadvantage of P's is the desired rate is unlikely achieved through this kind of approximation. And then one node is really not enough to recover the holes when the system sustains when there are no active nodes within the probing range of a redundant node. And it has loose guarantee of the time of recovery, which we will see in the simulation. So first, we evaluate the fault tolerance of schemes. So in this particular graph, we fix the failure period at 5,000 hundreds, and the delta will be 50 seconds. So as we can see, as the failure percentage goes up, so 90% of lifetime goes down, which expected. And we can see R-Sentry outperforms at each of the scenarios. So this is because with R-Sentry coordinating the wake-ups of the redundant nodes, it always could have enough nodes to keep the network percentage above 90%, and it could always recover from the death of active nodes. Well, P-Sentry and R-Sentry couldn't have this have enough nodes available. And then, if we look at the plot on the right, we'll see R-Sentry nicely keeps the average coverage recovery time around the delta. However, we don't see this kind of feature from P's and P-Sentry. So now in this set of plots, we fix the failure percentage at 5%, and then we vary the failure period. And as expected, as the failure period goes up, the lifetime of all three sentries goes up. But again, at each particular set of scenario, R-Sentry outperforms the other two sentries. And then again, R-Sentry does nicely in keeping the average recovery time around the delta time as designed. So, other than the extended network lifetime, the configurable recovery time delta is a nice feature. Is a feature R-Sentry has, while other schemes don't have. So here we fix the failure period at 5,000 and the failure percentage at 5%, and we increase the delta. So you can see before the point where delta is 400, the lifetime pretty much keeps the same. That's because R-Sentry can keep the nodes wake up relatively in time, and when the delta becomes big, the redundant will still longer to consume more energy. But when the delta goes to 600, the lifetime of the 90% lifetime drops significantly. Why? That's because we believe if the delta goes up, the chances that during one specific period there are not enough nodes to keep the coverage above certain percentage. And this also has to do with this simulation methodology we use, because we start the simulation when the coverage drops below 80%. Because we think once the coverage drops below 80%, we don't think this network is usable. So because of that, when the delta is 600, we don't have, at a certain point, we don't have enough nodes to keep the coverage above 80%. So this is why the network lifetime drops significantly. And then, if we look at the coverage recovery time, we will see again for R-Sentry, as the delta goes up, the average coverage recovery time goes up as designed. And while P is still, even though P is claim they can control the probing rate using user length, still it fails to fool the promise. To scalability. In wider sense network, people intend to deploy more and more sensors, hoping to be able to take advantage of this redundancy to extend the network lifetime, given using this shift-based protocol. So in here, we increase the node number. You look at how the schemes forms. So on the left plot, the node number goes up. All the three schemes has a longer network has a longer network lifetime, which means all the three schemes could take advantage of the extra nodes available to increase the network lifetime. And then on the right side of the plot, we'll see that the node number increases, P's has a relatively stable wake-up frequency, while R-Sentry has a relative the wake-up frequency increases modestly as we have more and more number of nodes. The reason why here is because we see the R-Sentry has a long lifetime. So during the late lifetime of the network, each node has less energy, and the whole system is becoming more dynamic than in the first half of the network lifetime. So during the late part of the network lifetime, there will be more active nodes dies, and more redundant nodes to take over, and then those redundant nodes already has less energy than the redundant nodes in the first half of the lifetime. So there will be more network dynamics, which causes a rather frequent, rather big wake-up frequency. So really, what is behind the scene for those nice feature R-Sentry enjoys? So here we print out the time series of the coverage and the number of active nodes for both R-Sentry and the P's. In this plot for R-Sentry, we'll see R-Sentry nicely keeps the number of active nodes pretty much as 10% of the overall number of nodes, and the coverage is rather close to 95% all the time. And those spike means those events that active nodes dies and the redundant nodes take over. And then for P's, we'll see. Initially, there's a big drop in here. What happens here is that's when the initial set of active nodes dies because of low energy, low battery, and then it will gradually climb. The number of active nodes will gradually climb up to recover. Then it keeps going down to the extent that the coverage percentage drops below 80%. This only means P's cause the redundant nodes to oversleep. So greater size is virtual. It shouldn't affect the performance of our schemes. But R-Sentry use greater points to measure the coverage and also make a decision based on the current coverage. We do experiments with greater size as 1 square meter and with greater size as 5 square meter. So we'll see. For P's, performance is pretty much the same regardless of the greater size, because P is really not dependent on the greater size. P In P, the node decides the states based on the probing range instead of the grid size. But for R-Sentry use the grid size to decide the number of the active nodes. So remember, in the initialization phase, we decide who should become active, and if needs to be active based on if all of its grid points are covered. So the bigger the grid size, the less grid points in the system. So the less active node we need. By R-Sentry.
So what does G1 or G5 mean?
G1 means the grid size is 1.
And
G5
G5
means the grid size is 5
square meters?
Yeah, 5 square meters, yes.
So it's like 2.5 meters on this, there's like a, so there's some smaller, it's like it's a 2 meter radius or something, or pi r squared, like a 1.5 meter radius for 5 square meters. The coverage area is like a circle.
Yeah, coverage is like we partition the whole network into virtual grids.
Right. So what happens if you went to G20? Like, would it matter then to both of them? I mean, it's kind of weird that it doesn't matter to P's to me.
The P's itself is not dependent on the grid size.
So we get the same result if you had a 20 square meters grid for P's?
Yes, because the difference is in P's, the node decides the states based on the probing range. So when the redundant node wakes up, it will probe the active node within a certain range. So if the receiver reply, it goes back to sleep. If it receives nothing, it becomes active. So the state of the node is not dependent on the grid size. But in R-Sentry, when node wakes up, it will probe, and it will receive response from all the active nodes. Then it will take a look of if all my grid points is covered or not. If not, I should go active. So that makes a difference between P and R-Sentry. So gain size. This is really a key point of this gain-based scheduling. So if we look at this plot, we increase failure percentage, right? And again, general trend is as expected. The lifetime should go down, but we'll see the R-Sentry with gain size of 2 outperforms the R-Sentry with gain size of 1. Why? Because here we have random node failures, and when the gain size is 2, even though a percentage of those redundant nodes die, still we have enough redundant nodes to monitor the active node and to take over as needed. But when the gain size is 1, we'll have relatively less number of redundant nodes available to do the job. So that's the reason why the gain size of 2 outperforms the case with gain size of 1 a little bit in this plot. But the performance gain is not as much as we initially thought. This, I think, is because of the fact that first, active node is overlapping in terms of the active node coverage. So neighboring active nodes obviously share the coverage. Okay? So one certain grid point could be covered by multiple active nodes. The second is they also share redundant nodes. So even though we have less redundant nodes, because they could be shared by multiple active nodes, so the overall impact, overall benefits with the larger set of gain, it's kind of discounted because of this share. But if we look at the plot on the right, as we increase the delta, then for the R-Sentry with gain size 1, it's the same as in the previous plot, that when the delta increases to 600, the lifetime drops significantly. But in the case with gain size 2, it doesn't happen. Why? Because we have more redundant nodes, right? So there will be also less chance that there will be a period where we don't have enough nodes to keep the network coverage above certain percentage. So far, every node is a good guy. They do what we told them to do, and they are compliant. But what happens if certain nodes don't cooperate or even compromise? So in the second piece of the presentation, I will talk about the security issue in R-Sentry. So obviously within the network we have some generic security attacks, like denial of service physical attack and the node directory attack. So those generic attacks apply to any network. But here, we want to focus on the R-Sentry. We want to focus on the attack that is specifically coined against R-Sentry. We'll talk about two types of attacks. First, the passive attack. The second is proactive attack. So passive attack. In the passive attack, the malicious active nodes, they don't report sensor reading at all. But they pretend that they are still operating as normally, and they still respond to the probing nodes, probing from redundant nodes. And they still send a schedule as instructed by the R-Sentry. And they stay active until they run out of the energy. And so what's the consequence? The consequence will be service hole around the compromised active node. They will be recovered until this compromised active node dies. So take a look at this example. At time 1200, node A is compromised, so it stops report sensor reading, and however it still responded to the probing from all of its scans, and this malicious node keeps up until at time 2850. So we will see between the time 1200 to the time 3000, the grid points covered by node A are actually not covered at all. And the time between 1200 and the 2850, the coverage hole between this period is purely because this node is compromised. So what do we do? One obvious approach is we try to detect it. And one way we can do it is in the base station, we can analyze all the sensor readings it collects from all the active nodes. And because they are overlapping internal coverage, so we can compare difference of the same spot from different active nodes, and we can detect either. But that kind of involves the traffic, the technical readings and all the other related, and it will be dependent on the base station. So we want to step back. We don't want to detect it. We want to be proactive. So we can assume from the very beginning, okay, there could be compromised nodes. There could be nodes that stops reporting sensor reading while still generating schedules. So we want to impose a limit on the continuous active time, beta, through preactive scheduling. Specifically, each active node must go to sleep after it reaches this quota. So we use the same example in here. Suppose now the active node must sleep at the time about 1950 because it reaches the quota. It has to go to sleep. So this way we'll see the coverage loss time has been reduced to 900 instead of 1800 without this preemptive schedule. So this greatly reduces the average loss recovery time. So we use the same some discrete event simulator to simulate this preemptive R-Sentry. And instead of the catastrophic event failure model, we introduced a malicious node distribution model. In this model, certain percentage of the total nodes are malicious, and the malicious randomly spread across the network following a uniform distribution. And the malicious nodes, they operate undetected and until the battery drains out. And in this set of simulation, first we fix the percentage of the malicious nodes, and we'll see as the percentage of malicious nodes goes up. Surprisingly, the 90% lifetime is kind of stay constant. Why? That's mainly because first, the percentage of malicious nodes are relatively small. And I believe as the percentage of the fault nodes goes up, definitely the lifetime drops down. And then secondly, because of the share because of the coverage overlap among the active nodes. So even though certain percent of active nodes are not covered, are not reported sensor readings, because some of their breakpoints could be covered by other healthy active nodes. So the overall coverage ratio kind of is on half. But what is the benefit of preemptive R-Sentry? So if we look at the plot on the right, we'll see R-Sentry fails to keep the promise on the delta average coverage loss time. But preemptive R-Sentry nicely keeps the average coverage loss time around the delta. So what is the impact of this limit of this quota in the preemptive R-Sentry? To find out, we did a set of simulations with different quota. So here the beta again is the maximum continuous active time of each active node. We will see as we increase the beta, the network lifetime not change too much. Why? Because even though the beta changes, beta increases, still because of R-Sentry making the redundant nodes to wake up every delta. And this delta and the gap between any consecutive is not affected by this beta. So this beta should have a much impact on the network lifetime. But it does have an impact on the coverage recovery time. So we'll see as we increase the beta, we give the malicious nodes more time to harm the system. and as a result, the recovery time goes up beyond the delta. So in the passive attack, the malicious nodes, they kind of just implicitly stay there doing harm. They don't do any. They don't try to manipulate. They don't try to change anything. They are just refuse to do something. So that's why we call it passive. And here we want to talk about what happens if a malicious acting node try to be proactive, try to manipulate schedule, which is a cornerstone of the R-Sentry. So here we want to look at the two modes of proactive attack. First is secretive mode. In the secretive mode, the malicious acting node manipulate schedule, hoping to cause oversleep of redundant nodes, but it changes schedule modestly, hoping it will not be detected. But in the second mode, the brute force mode, the compromised acting node will change schedule drastically. It doesn't care if it will be detected or not. It just hopes to stop redundant node from waking up. So in the secret mode, the behavior of the attacking node is the attacking node do not report sensitivity as in the passive attack, and the compromised acting node just send modestly change schedule by increasing the delta modestly, and the identity obviously well concealed. And so what is the defense? Here the defense again is preemptive R-Sentry. Why? Because preemptive R-Sentry for the passive attack, during the secret mode, we cap the continuous. We defense by capping the continuous active time. And for the modestly manipulated schedule, it's very similar to a scenario with a larger delta. So, and we already see that R-Sentry performs well, at least in terms of network lifetime, when delta becomes big. And obviously, we don't worry about identity detection here. And for the proactive brute force mode, because it's brute force, right? Because it doesn't care if it will be detected or not, and their attacks are always obvious, but they don't care because it's effective. And in this attacking node, the malicious acting node schedule its redundant node to sleep excessively long. But they don't attack in sleep mode. So that means they still wake up and schedule when they are redundant nodes. And schedule manipulation is the only means of attack. So what is the defense? First, we need to detect the invalid schedule. Second, we want to randomize the schedule based on available information in the presence of the invalid schedule. As we will see, R-Sentry really, to make R-Sentry work, we really need a delta against side. Then the sensing related set. But because of the invalid schedule we receive from the active node, the malicious active node, we don't have information on this sensing related set of that particular active node. So that means we cannot figure out how the redundant node cannot figure out how long it should sleep. So the answer is a randomized R-Sentry, which is inspired by the random replacement algorithm in virtual memory management of the system. In here, we just want to make sleep interval scheduled by the complement active node as a uniform the random variable. Here the change is what is lower bound and upper bound of this random schedule. Lower bound will be delta. Why? Because even in a complete R-Sentry, the lower bound is delta. The upper bound initially it's not available because it's supposed to be from the active node, but active node has invalid upper bound, so we cannot use it. But still, there's some valuable information that is available, readily available by deduction. First, current network lifetime. So obviously we can have this from our internal timer. Second, the remaining function nodes. How do we get it? So so obviously we already know the current network time, and then we can know how long active node can last in active mode based on some historical information, and then we can know the number of active nodes that needs to be available to provide the required coverage percentage. So given that, we will know how many active nodes have served the system until now. And those nodes obviously have died because of the energy, because they don't have the energy is drained out. So we minus this number from the current number of nodes, the total number of nodes, we get an estimation of the remaining nodes. The third is remaining network lifetime. So again, we have the number of remaining nodes. And then we sort of know how many active nodes the system needs to have to maintain the coverage percentage. And then we time it by the active node lifetime that could sustain with the current energy. Then we get the remaining network lifetime. The fourth one is the remaining lifetime of the redundant node. So again, obviously each run node know its energy level. And then you have an idea the energy consumption pattern based on historical information. So we can get the remaining lifetime for this redundant node. And the last, we have the average number of redundant nodes of each active node. How do you get it? So first, we know we already deduced the remaining nodes, and we already know the size of the initial the number of active nodes in the current system. So based from this, we can know the number of redundant nodes in the current system. So we divide it by the current number of active nodes. So we get the estimation of the redundant nodes each active has. And then we time it by a factor to reflect that the active nodes could share the redundant nodes. So now we have remaining network lifetime. We have the remaining node lifetime. Then we have the average redundant node that each active node has in the current system. So we will choose the minimum of these three values as upper bound. So the underlying logic is, first, the redundant node will not be able to contribute if it sleeps past the network lifetime. Second, the redundant node won't be able to contribute if it dies during sleep. Third, the redundant node shouldn't sleep longer than the delta times average of the redundant node, according to R-Sentry. So first, let's look at experimental results for secretive attack. So we introduced a new parameter called delta scale. this is a scale-up effect for delta. And whenever the malicious act node wants to generate a schedule, it will scale up the delta by delta scale. So we'll see as the delta scale increases, R-Sentry looks fine. However, the preemptive R-Sentry suffers the same problem with R-Sentry when the delta is beyond a certain point. Again, this is the same reason because of this preemptive R-Sentry has a relatively frequent state transition. There's more chance for the system to have a gap where they don't have enough active nodes to maintain the coverage ratio. But for R-Sentry, we already see in the previous plot, when the delta goes up, the network lifetime of R-Sentry actually stays constant. But the benefits of the preemptive R-Sentry is it keeps the coverage recovery time around the delta. But as we'll see,
You may want to speed up a little bit.
So now let's look at how the 40% affects the security attack. As the percentage goes up, R-Sentry has a good lifetime, network lifetime, but preemptive R-Sentry drops down significantly. Why? That's because as the percentage, 40% goes up, again, there's more chance for the preemptive R-Sentry has a period where they don't have enough active nodes to keep the coverage ratio above a certain percentage. But again, preemptive R-Sentry provide the benefits of the constant coverage time. So now we look at how the brute force attack played out with the random scheduled R-Sentry. So as we increase the 40%, we will see R-Sentry initially works fine, but when the 40% is larger than 40%, the lifetime drops significantly. That's because R-Sentry don't have because a lot of the dumb nodes don't have an idea how long it should sleep. So it doesn't have valid schedule to follow. So the network lifetime falls down. But with a random scheduled Sentry, the lifetime stays constant. Actually, a slight improvement. Why? Because around at this time, the random scheduler takes over for certain redundant nodes, and to make sure the performance, we kind of keep the up bound of the random schedule a little bit small, so that the node could wake up rather frequently to keep the network covered about a certain percentage. And in the plot on the right, you'll see as the percentage goes up, R-Sentry suffers in the coverage recovery time. But the random scheduled Sentry actually does pretty good. Okay, so now I'll give a brief summary of all the schemes I have presented. First, the P-Sentry. In P-Sentry, the dumb nodes divided into two groups. Each group serves a different purpose to help extend the network lifetime. But for R-Sentry, group of dumb nodes in GANs and schedule them to wake up in turn periodically. And the schedule is carefully crafted and active nodes lead to prolonged lifetime and bounded average coverage recovery time. And for preemptive R-Sentry, a variant of R-Sentry that imposes quota of continuous active time that leaves the impact of passive attack nodes. And with random scheduled R-Sentry, That's another rare philosophy that employs the randomized scheduling when no valid schedule available due to brute force attack or any other reason. So we have a context aware outbound helps generate a random schedule that reflects the current network state. So here I will talk about some relative work. So Sent is a similar shift-based schedule. In Sent, a node decides its state based on the information around its neighborhood, like number of active neighbors, packet loss ratio. The issue with the Sent is it's collector-oriented. It requires knowledge of the traffic pattern. And in each node experiences 4 states before it becomes active. And at each stage, like test, passive, it has to keep up for a while to collect enough information before make a decision. So sometimes this will cause inertia or thrashing between back and forth between test mode and passive mode. Then we have the ODDC. So the ODDC, the whole lifetime of network is divided into rounds. Node selection takes place at the beginning of each round, with all nodes up. And node selection to be active, each node is selected to be active under the framework of geographical optimization. So there's a lot of geometric computation involved. And this is rather complex and very heavy. And most importantly, random sense failures are not taken into account in the design. The third one is a differentiated surveys for sensor network. This is again a random-based system, and the schedule during the whole constant network is set at the very beginning of the lifetime, and it will wake up when the active node is detected dead, it will wake up all the sleep neighbors to recalculate the schedule. So the disadvantage is it needs a separate wake-up radio to recover further active. And the extra overhead in recalculate schedule whenever active node dies. So during my case study period, I did my publication in here on wireless sensor network. And so I still need to submit my thesis work to the transaction on the sensor network. And then this is the publication I had in peer-to-peer when I was an intern with Thompson Research. It's mainly in peer-to-peer video on demand system. So this is the end of my presentation.
So, any questions?